I'm Anil Kumar. Welcome to my series on pre-calculus. We are discussing exponential and logarithmic functions. While logistic functions are a very important part, here in this video, we'll discuss what are logistics functions and how to find their domain and range, and also some interesting points to sketch such functions. Well, the logistic function is something which is sketched here. It looks like a S-shaped thing as shown here in the graph. It is always increasing or it could be always decreasing depending on the function as shown here. So we can actually say that it is S-shaped continuous curve for equation f of x equals to L over 1 plus a e to the power of minus kx with two horizontal asymptotes and no turning points. So in this particular case, as you can see, we have two horizontal asymptotes. One is the x-axis itself and the other one is the y value equals to the value of L, which is in the numerator of this particular function. Now, here we have few graphs. With the graphs, I also provided with the equations. You can look at these equations, correlate with the graph, and from there you will understand how this equation is related with the graph itself. So the idea here is to explore the characteristics of logistic function, identify the relation between the parameters L, A, and K, and the characteristics of the function, right? So you need to now understand from the given graph that we know that the function which we are defining is equal to L over 1 plus a e to the power of minus kx. So see how the values of L relate to the graph, the value of A relate to the graph, and the value of K relate to the graph. You can clearly see that if this value is 8 on the top, then the horizontal asymptote is also at 8, right? So these two indicate that. So that means y equals to 8 is a horizontal asymptote. If this value is 6, then the horizontal asymptote is 6, right? So basically we can say from here that the range of the function is between 0 and the value of L, correct? So one thing which we could figure out is that the range of this particular function is between 0 and L. You can also notice that the exponent, if the k value is, let us say, greater than 0, in that case, what is happening to the graph? And what happens when k is less than 0? Well, if k is greater than 0, in that case, we'll see that the graph is increasing, and if k is less than 0, we see that the graph is decreasing. Well, k is less than 0 for this particular graph, where you can see that the graph is decreasing. In all of the graphs, the value of k is greater than 0. So that is how it is kind of related. Now let's explore the value of a. From the equations, you will notice that the value of a is 1, 1, 1, but here we have a value of a which is 5. Now, what really happens here is that the center value of the graph, you can see the concavity changes at a point which is normally at the center value when the a value is 1. So if a equals to 1, in that case, the center value is the point where the concavity changes. However, if the value of a is not equal to 1, in that case, the concavity changes at a point which is much lower than the center. So we can say that if the value of a is greater than 1, right, in that case, the point of inflection, this point where the concavity changes, is less than half of L, correct? So something like this we could correlate. Now we are going to mathematically check all these values and understand the application of this particular function? Well, it finds application in many industries, especially wherever we are doing culture of living things. So, for example, if you're running a fishery, you will know that feeding will help them grow. However, there is a stage after which it is better to sell the fish rather than to feed it more, since after that it may not be so profitable. So the point where we have got the increased size of the fish, that is a critical point. So rate of growth is kind of important, and we'll see how we can check the rate of growth from this particular graph. Now, let's look into domain and range of this particular function first. As you clearly saw, that the function is continuous all throughout, and also its domain has got no restrictions, right? So let's get back to our function, which is f of x equals to L over 1 plus a e to the power of minus kx. Now here you can see that the value of x could be any real number, correct? However, the value of y is in between 0 and L. So that becomes the range. So range of the function is clearly defined in between the two horizontal asymptotes, correct? Now, how do we really find these horizontal asymptotes? That is a big question. So now let's look into the horizontal asymptotes. Well, horizontal asymptote is the horizontal line which the graph of the function approaches as x approaches positive and or negative infinity, a very large value. So if the value of x is approaching positive or negative infinity, and the function is approaching a value, not infinitely large, but a defined value, in that case, we have a horizontal asymptote. So, let us see what happens when x is approaching negative infinity. When I substitute negative infinity for the value of x, we notice that e to the power of minus kx will approach infinitely large value. And that means you're dividing by infinitely large value. This is in the denominator, right? And therefore, L divided by a large value will result into a much, much smaller value. So the value of the function approaches 0. Since x approaches minus infinity, value of the function approaches 0, we have a horizontal asymptote y equals to 0. Does it make sense to you, right? Okay, now let us check the second scenario. When x is approaching positive infinity. When x is approaching positive infinity, e to the power of minus x will approach 0, right? E to the power of minus kx. It is going to approach 0. And so this term, a times e to the power of minus kx, will also approach 0. We are left with L over 1, which gives us the value L. So the function approaches L. So therefore, we have a horizontal asymptote y equals to L. So in this case, when x is approaching positively large value, in that case, the function is approaching L. And therefore, we have the horizontal asymptote L. So that defines your range between 0 to L, correct? So we come back to our range question. So the range of this function belongs to R, where f of x is between 0 and L. So, logistic functions is used in studying population growth in constrained environment where L is also defined as the carrying capacity. Maximum limit is L, right? So, as you have seen, that the function is basically defined between these two limits. And in general, it is kind of increasing like this, right? That is what it is. So this particular point is the point which is called point of inflection, and you can see that the rate of growth, which is the slope, is highest at this point also. And this point here is called the carrying capacity, right? So the value of the function cannot be even equal to that, but it approaches this particular value, correct? So in the industry, we say this is the carrying capacity, the maximum possible value which can be attained. So in logistic function is used in studying population growth in constrained environment where L is also defined as the carrying capacity as it indicates the maximum limit of the function that is approached. Is that clear to you? Right? So that is the maximum limit of the function. So now we understand that the domain is all real numbers. However, the range is limited between 0 and L. Now, let's talk about the point of inflection in more details. When we look at this graph, we see that initially it increases very fast, like an exponential function, right? So, initially the graph of the function rapidly increases like an exponential function. Then it becomes linear. So you can see that in the middle portion, it is kind of a straight line. So then it becomes linear, right? After about halfway, declining growth rate levels out the curve and approaches a limiting value. So at the end, after this half point, we see that it is like a decreasing growth rate approaching the maximum carrying capacity. You see that, correct? So the point right in the center, which is halfway between, this is L by 2, correct? So this is the point which is halfway where this is L, the maximum value which it can achieve. After the halfway, the growth rate decreases. That is what you can see in each and every graph, right? Where k value is positive. Of course, when k is negative, we have a decay, but it is a similar function. Initially, it is exponential, then a linear, at the end again exponential, right? So that is how it is, as you can see. Now, after about halfway, the declining growth rate levels out the curve and approaching limiting value, right? So that is what we're trying to say. The concavity of the graph changes at one half of the carrying capacity. This point is the point of inflection and is the steepest part of the graph. It signifies the maximum growth rate. So let's understand this concept. So as you can see, the initial part of this is concave up, right? So this portion is what we say is concave up, correct? And the later half is concave down, right? So this is, so at this point where the concavity changes is called point of inflection. So you can see that the rate of change is almost vertical line here, right? It is extremely steep. So this is steepest. So that shows highest or the maximum growth rate at this particular point. And therefore, it is a very, very critical point. So at this point, we have already achieved the halfway of the carrying capacity. And at this point, we have also achieved a maximum growth rate. So as you can see here, that the concavity of the graph changes at one half of the carrying capacity. This point is the point of inflection and is the steepest part of the graph. It signifies the maximum growth rate. Clear? I'd like you to take a moment and correlate these graphs with the equations given here. That's a very important exercise. You can also estimate the point of inflection in the particular examples, right? So the point of inflection in these cases is right at the middle. However, here the point of inflection is still at L over 2, but the y value is different. So you can explore approximately how much this y value is. And the reason is that here we have a value which is not equal to 1, which is more than 1, and therefore we see that the y-intercept is not the point of inflection. Now let's look into the questions related to this particular topic. I hope you have got the concepts. I will now like you to pause the video, answer these questions, and then look into my solutions. Question number 1 here is, find the point of inflection for f of x equals to L over 1 plus a e to the power of minus kx. So I've taken a general function so that you can derive a formula, and this formula can be applied to find quick solution. Part B is use the solution in part A to write the point of inflection of f of x equals to 8 over 1 plus 5 e to the power of minus 3x. Clear? Now let us see how to find the point of inflection. Strategy is very clear. Since we know that the point of inflection is at a point where the value of the function is half of L. So the very first step here is, in this particular equation, for the function which is half of L, we'll put the function values L over 2, equated to L over 1 plus a times e to the power minus kx. And now, clearly, we can now equate the denominators to 2. So 1 plus a e to the power minus kx is equal to 2. Taking 1 to the other side, 2 minus 1 is 1. We get a times e to the power minus kx equals to 1. Now we can divide by a on both the sides and get e to the power of minus kx equals to 1 over a. Correct? You can take log both sides now. Remember, ln e is what? Ln is 1. So we took log on both the sides. We'll take natural log whenever we are working with e, since ln e is 1. Now, we'll apply the power rule at this place. Power rule, I hope you remember, ln a to the power of b is b ln a. So you have to revise your skills on logarithmic functions, correct? Now in this particular case, if you're talking about ln e to the power of b, it will be b times ln e. As you know, ln e is 1, it will be equal to b. And therefore, in this particular case, what is b? B is minus kx. So ln e to the power of minus kx will be minus kx. Perfect? On the right side, we get ln 1 over a. Now, minus x is equal to 1 over k, or you can say x is equal to minus 1 over k, ln 1 over a. We can now apply the power rule once again and write it as 1 over k ln 1 over a to the power of minus 1, or we can write down the formula x equals to 1 over k ln a, right? You remember ln 1 over a is basically minus ln a, right? So that is how we come to the value of x. So since we now know the value of x, we can write that the point of inflection is 1 over k ln a, and the y value at this point is L over 2. Correct. So we got the point of inflection, and that is the standard formula for logistic functions. Now let's find the point of inflection for the given equation. Now in the given equation, we are given that L value is equals to 8 and the k value is equals to 3 and a value equals to 5. Substituting that, 1 over k means 1 over 3, right? And ln, value of ln a is 5 for us. So we get ln 5, half of 8 is 4. So we get a point of inflection straight away. So from the given formula. So I hope that makes sense. Correct? And that gives you the center point right there. So we have this point which is at 5, and we got the x value, correct? In this case, that is a general graph. So in this case, we're talking about 8. So let us say this is 8. In that case, this will be at 4, right? And the point here will be 1/3 of ln 5, the x value. Perfect. Now let's take the next example. In question number 2, the question is to sketch the graph of y equals to 10 over 1 plus 2 e to the power of minus x, showing all asymptotes and any 2 points. Correct? So let's try to do this. Now clearly, in short, we know two things. It is a graph between two asymptotes. One of the asymptote is the horizontal x-axis. The other one is the value of L. Now in this particular case, The value of L is 10. So we can write L equals to 10 as this horizontal asymptote. Perfect. We also know that the denominator, the value of k is positive, and therefore the function is increasing. The value of a is 2. That means that the y-intercept is below the half center point, and therefore we are expecting a graph which is kind of like this. Is that clear to you? Now the 2 points which we have to find, we could find the y-intercept and we can also find the middle value. Middle value, you can use the point of inflection formula value and then write it down. And for the y-intercept, what are you going to do? Substitute x equals to 0 and find the value. Perfect. Now, here once again, what I've done here is I've found the horizontal asymptotes using the concept we actually applied earlier. When x approaches minus infinity, 2 times e to the power of minus x approaches infinitely large value. Therefore, f of x approaches 0. When you divide by a very large value, what do you get? You get 0. So that is your horizontal asymptote x equals to 0. Now the second, y equals to 0, right? So this is your horizontal asymptote, which is y equals to 0. So at any point on this line, the x-axis, the y value is 0. Now what happens when I put positive infinity for x? So definitely e to the power of minus kx now becomes infinitely large. And therefore, we get f of x, this becomes infinite, this approaches 0. E to the power minus kx, right? So when you put infinitely large, so it becomes 1 over e to the power infinity, right? And so that approaches 0. Clear? So therefore, this particular term approaches 0 in the denominator. And therefore, it is f of x which approaches 10 in this particular case. Correct? Now, the horizontal asymptote, since it is approaching 10, is at y equals to 10. So one of the horizontal asymptote is at y equals to 0. The other one is at y equals to 10. Now the carrying capacity is the horizontal asymptote y equals to 10. That is the maximum value which this function can achieve. Approach, I should say. It is never 10, right? So y-intercept in this case, now let us see how to calculate. Substitute x equals to 0. So e to the power of 0 will be 1. So we get 1 over 2 in the denominator. 10 divided by 3 is the y-intercept. So this particular point here will be 10 divided by 3, correct? So let me write down this point here as 10 divided by 3. For point of inflection, we can again do our calculation. That is to say that the denominator should be equal to 2. Since the point of inflection happens to be at the midway, right? Half of 10 in this case, right? So the value will be at 2. So 1 plus 2 e to the power minus x is 2. Taking 1 to the right side, 2 times e to the power minus x is 1. E to the power minus x is half. Taking ln on both the sides, we get minus x equals to ln 1 over 2, or x is minus ln half or ln 2. So we do get this point, which is ln 2, and the y value is half of 10, which is 5. And so we get our 2 points in the shape of the curve, carrying capacity, half carrying capacity, and both the horizontal asymptotes. So with that, we can sketch our function, which is shown right there. Is that clear to you? With 2 horizontal asymptotes. Perfect. Now, you need to write the domain and the range. So domain of this function is all real numbers, no restrictions at all. Range of the function is that the y value is between 0 and 10. Is that clear to you? Now the last question here is to match the equations with the graph. A, y equals to 4 over 1 plus e to the power minus x. B is y equals to 4 over 1 plus e to the power of x, and y equals to 4 over 1 plus 7 e to the power minus 2x. D is 4 divided by 1 plus 3 e to the power of 2x. So you can now match these graphs. Um, take your time, and here is my solution. So we are going to see that the a values in these two cases, we see that the a values are 1, right? So a equals to 1 in both these values. Second, what we notice is that the k value in this case is less than 0. In the first case, k is greater than 0. So that means the graph has to be increasing. Y-intercept is on the y-axis. So that matches with our first graph itself, where the center point is at the y-intercept, which is the point of inflection. Now the second one, because the value of k is negative, it is decreasing all the way, and the center value is at the y-intercept, the point of inflection, right? So that matches. Now let's look into the third. 4 over 1 plus 7 e to the power minus 2x. K is greater than 0, right? Since k is greater than 0, we are looking at an increasing function. This is 7, so that matches. So it matches with that particular graph. And now let's look into the last equation, which is 4, 1 plus 3 e to the power of 2x. So in this case, the value of k is less than 0, and so it is decreasing function. And we also see that the value of a is greater than 1, and therefore the midpoint is, the y-intercept is below the mid value, right? So that is how you could match your graphs. So I hope you have a clear understanding of how to correlate this particular logistic equation with the graph. Now let us summarize with some key concepts. So we learned that the logistic function is given by the equation f of x equals to L over 1 plus a e to the power of minus kx. It is a smooth S-shaped curve with two horizontal asymptotes which are at y equals to 0 and at y equals to L. Function is always increasing if k is greater than 0. It is decreasing if k is less than 0. Now, the y-intercept of the function you can easily find by substituting x equals to 0. If you substitute x equals to 0, then we get L over 1 plus a as the y-intercept. L is the maximum value being approached, right? You can never be there. It is called the carrying capacity, is the limit. Now, point of inflection is the midway between the maximum and the minimum values being approached. So you can directly find the value of the coordinate value of point of inflection as 1 over k ln a, the x value, y value being half of L. So it is also the half of the carrying capacity, right? Now y-intercept is a point of inflection if a is equals to 1, as we have seen in many of the previous graphs. Now, the constant a you could find by substituting the value x equals to 0. We get f of 0. So look here, from this particular equation, what is f of 0 equals to? You can substitute 0 for x, so you get 1 over 1 plus, if I substitute 0 here, we get 1 plus a. Now you can cross multiply, so you get 1 plus a equals to 1 over f0, right? So value the function when x is 0. So clearly a equals to 1 over f0 minus 1. Does make sense to you, right? So that is how we get that the constant value of a is given by 1 initial value f of 0 minus 1. Now, this equation is so popular and you find many applications of this equation. So one of the standard logistic function is when a, L and k all are 1. So the function can be written as 1 over 1 plus e to the power minus x. So 1 over x, let me rewrite this for you. So we have f of x as equals to 1 over 1 plus 1 over e I can write to the power of x. Minus means the same thing. So if you take the common denominator, you get e to the power of x plus 1 over e to the power of x, or you write this as e to the power of x plus 1. So that is what we did. So this is called the standard logistic function, right? Another important thing which you notice here is about the symmetry. You will notice that f of x minus half is the odd function. So it has odd symmetry when you shift to this particular point, right? So if you see from this particular point of view, from this point, it has the odd symmetry, right? So it has the odd symmetry when you translate your function to the point of inflection. Does make sense to you, right? So that is what we conclude here in this particular video. I hope you learned a lot. Feel free to write your comments and share your views. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.